Hi everyone, I'm Jithin from Microsoft. So today we'll be talking about designing scalable networks for AI clusters, some of the challenges in scaling beyond, and what are some of the key insights from our experiences so far. So at Microsoft, my team and I, we focus on designing and building the backend network for large-scale AI clusters, developing communication libraries with the focus of exposing the key hardware features and the key network features to the middleware or the training applications, and some of the performance optimizations at scale, right? So those are our focus areas. So with that, I would like to get started, and I would like to get started with some of the scaling journey and breakthroughs. So, like many of you here, right? I mean, we also started heavily on the HPC side of things. By HPC, I mean the traditional scientific codes like the MPI application. So back in 2019, like we were the first cloud to hit the 20K scale MPI job mark, right? This is again first for cloud. And then later, like with HDR, like we even bumped it up like to about 80K job again, like first for cloud, and then we really look at like the performance and scalability, and especially like scaling efficiency. And then things really took off with the NDV4, Azure NDV4, with the NVIDIA A100 and the HDR machines. So together with OpenAI, we built large-scale AI training clusters, and we even took it to in the first few ranks, within rank 10 for the different top 500 supercomputers. And then, like, we even took it further with the NDR and H100 clusters. So last year, we got like rank number 3 overall. Again, number 1 for cloud in top 500. And again, number 1 for ML Perf and rank number 2 overall, right? So I'm happy to share that I led the team for the top 500 submission and also led the backend network designs or optimizations for the ML Perf runs, right? So yeah, it's a really interesting time that we are in, right? So back in the days when I was in grad school, like we were always, whenever we see a paper about like, hey, 1K or 2K GPUs, like we were like, oh, wow, they got a really large GPU clusters. And now we are in a time where we see like CEOs posting about, oh, really multiple thousands of GPU scale for their jobs, right? But yeah, we are actually like not, I mean, stopping there, right? The AI training continues to push the scaling boundaries, right? I mean, we all know that the race is on. The accuracy and performance requirements are still going up, right? And the AI market is actually really getting diverse, right? So eventually that leads to like larger and diverse data, and the models are getting more complex, right? And as a result, I mean, everything goes back to the need for larger scale, right? So in this talk, I'd like to talk about what are some of the challenges that we see in scaling beyond and how we address those. And I also want to set the scope for this talk. So we are from the platform and networking side of Azure HPC AI. So in this talk, we'll talk about network topologies, routing designs, communication libraries, etc., but not a lot on the application or the model optimizations or other performance characteristics of the jobs, right? So yeah, so let's dive into this, right? So we'll start with some of the challenges here, right? In scaling beyond, starting with I mean, how we build the network, or how we design and build the network topology, and then like once we build the network, how do we validate it? Because these are large clusters, maybe built in chunks, right? Some of the communication library optimizations that we look at, and then how efficiently or how reliably this cluster can run for the training job. Okay, so let's start here, right? Building the network topology. As we know, the scaling requirements are like immense, and then these are actually pushing the switch radix to much higher, right? I mean, like we can again build really large clusters with say multiple layers or even like high oversubscription, but it may not be really good for the train, right? So how efficiently we can do that? And there are multiple ways. I mean, we can get around that. Maybe multiple planes, or maybe rail optimized, or maybe a combination of both, right? But again, we need to look at, how these all work for, or how good are these for the different workloads or workload characteristics, right? And you can always look at the planes or rails merged at the top layer, or like keep it rail only, right? So, can it support the different the network characteristics, right? And then you can always design multiple network ports and then all connected with a high oversubscription, or maybe a single port, right? Again, like we need to look at, the workload requirements, right? So, network fungibility is another main thing, right? So we build this, really super expensive network, and but if this works only for workloads of say this era, right? Then that may not be a good design, right? So we need to like look at where things are evolving, right? And network. So that's why network fungibility is actually a big point, right? And another main challenge is about validating the cluster. So we build this cluster, but the cluster may be coming up in different chunks, right? And because these are like super expensive machines, so we don't want them to be sitting idle, right? So we want we want to start training, or like some preparations for training as soon as possible, right? And the bringing up new chunks, right, should not impact the ongoing training, or like some of the workloads or benchmarking on the new chunk should not impact the other ones, right? So how efficiently you can validate that, right? So you may need sophisticated benchmarks to target your communication patterns like within that new chunk, and without interfering the other chunk where actual training is going on, right? And you also, there are a lot of routing challenges that we see, right? So in here, I have listed three pointed insights, right? So the first one is actually comparing two different generations of a network type. So here we can see the red one is actually all the generation one, and they're actually able to hit to the peak bandwidth almost instantaneously, right, within a few milliseconds, right? But however, right, the generation two takes a really long time to hit to the peak bandwidth. And this is actually very critical for training workload. As you know, the training characteristics actually maybe like a lot of times it is on off. So yeah, if it takes really long time, then you are actually degrading your performance, right? So that's one thing. The second one here, it talks about the multiple flows, right? Again, in training jobs, like there are like multiple flows. So in this graph, like we look at the bandwidth of each of the different flows, right? So what we saw is that the first flow was actually taking a long time to reach to the peak bandwidth, and whereas the other ones were actually able to hit to the peak almost instantaneously, right? And training like this is actually a very bad thing, because the slowest of the guys will actually determine the training performance, or the efficient the bandwidth, right? And the last one is showing about the routing efficiency when there are like multiple different paths that are possible, right? Or paths which are more than the actual the communication flow. So here we have like two sets of nodes talking between each other, and then you have like more than the number of pairs the network routes, right? So as we can see that when there are more paths, the performance is actually lower. And then once you try to disable the paths, then you see, the close to the theoretical peak number, right? So the essence of here of these slides is that, so sometimes we take these for granted, like, oh, these are like efficient routing, so so we can blindly rely on them. But we need to like look carefully into like, yeah, how efficiently these are routing, and then at scale, what is the behavior, right? And I'm not saying these are actually the open issues, like these are some of the solved ones, right? And then where we work together with our partners and go to the bottom of it, right? So, and then the next one is about communication library. And many of you know, right? The one of some of the very popular libraries are actually designed and tuned for a particular given network type and topology. And even though we may be running it on a different cluster with the same network type, I mean, the subtle differences, right, that make like impact on performance, right? So here I'm showing like two different graphs, right? I mean, where by proper tuning, we are seeing great improvements on the, like say, the message sizes, which are actually very critical for the training job. So the slide on the chart on the top shows good performance improvement for the message sizes which are relevant for the train. Another main key thing is that, I mean, the network state changes, right? I mean, so should communication libraries be agnostic about it, or like, or can it work together and get to a better performance, right? So those are other challenges that we are looking at. Also, and many of the times, right, I mean, power is very limited. So, I mean, you may have to, but the scale requirements is higher than that, right? So you may have to build DCs much farther apart. So how do you design communication libraries which are not based on round trip time, right? So those are our key challenges that we when we scale beyond, right? Another one is network reliability. So here I have two graphs showing, I mean, we have a training job run and then how that is impacted when we have link flag. So the first one shows the link flags between node and the switch, and the second one is between switch to switch. So in the first one, we can we change the duration of the link flag and then see what is the impact, right? So as you can see, the left one, you see a direct impact because there is no other path. But once we fine tune the timeouts, so we are actually able to still continue the job, but taking a performance hit. But on the right side, right, these some of the smart switch based designs, they're actually able to route it through different paths, so that when you look at the end workload performance, so we don't see any dip at all. But I mean, again, like we still need to look further, right? I mean, how fast the communication libraries are adapting to the network state changes, and also, like say, in when a particular link goes down, right? So it can cause network asymmetry. So how do we recover from that, right? So those are some of the other challenges that we see. And then again, changing gears, like we are looking into like, well, what are the some of the key insights and solutions that we have come up with to scale beyond, right? So here we are showing some of the topology designs. So we broadly classify the topology designs into two buckets: one for the public clusters and one for the dedicated AI large clusters, right? So the public clusters, we know, like we want to consider a wide range of model and their characteristics. So there can be communication characteristics like any to any or like within rail, etc. So we want to consider all of them, right? So for our public clusters, we are going with the rail optimized and also rail merged designs. So the advantage is that like any NIC can talk to any other NIC in the cluster. I mean, with almost equal bandwidth, right? So on the second graph here shows a any to any bandwidth graph. So we can see that all of them are actually hitting the same band of network, and which is actually the theoretical peak also. And on the right side, since we can design the clusters for particular workload, right? We know the workload characteristics, and we can take some over subscriptions and multipliers, right? So we look at say multi-pod based architecture, or even we also look at rail only architecture, or maybe merge some of those rails, right? So those are the directions that we are going with respect to topology. And then when it comes to routing, right? So I mean, we do like multiple approaches. I mean, the simple NIC plus smart switch, that's a very common approach that these days we have, right? It can also be a smart NIC versus simple switch approach. We have seen like many papers for that. But we are also taking a slightly different approach. So we are also thinking of a smart CCL approach or a smart communication library approach, right? So the key idea is that there can be snooping agents or events that we can collect from the network and which can be fed into a controller, and then the controller can give hints to the workload of the communication libraries during runtime, and then like adapt to the network state changes more efficiently, right? So And there are like again multiple ways you can approach it. Like you can maybe rely completely on the Nick side, or you can actually get hints from Nick and then do in coordination with the communication library, right? So like the smart RTT smart paper that is linked below is a very good example there. But we are also looking at derivatives of those designs where we can maybe like do further optimizations, right? And then coming to reliability, right? On the graph here is a very good example of, say, some of the smart switch-based designs, right? And then handling job resiliency, right? So here we have, again, like multiple pairs of nodes talking between each other, and then we take down links one by one. The great thing here is that the job was not impacted at all, and then like we can see the performance drop was directly proportional to the links, and again like based on the theoretical peak that we can achieve, right? So that was actually a good result. But there are like some of the key metrics that we need to focus here, right? So one key thing is that we can see when a link goes down, the performance drop is almost immediate, right, or instantaneous. However, when the link goes up, there can be a time delay that the CCL takes to get to the peak performance, right? So is that actually good enough, or do we need to do optimization? And then the key point, like we mentioned before, is that the link downs can cause network asymmetry and leading to congestion, right? So what happens is that like some of the existing designs or some of the things we need to take care is that we need to have a feedback to the source, and then the source can take multiple different paths to avoid those congestion points, right? Those are some of the designs which can gracefully handle this better. Another main point is we are also looking into like new tools where we can target specific links, the links which are like more relevant for satisfying the job reliability, right? Like we saw the server to switch link, right? That is one of the key pieces. But how can we target that one, right? I mean, you can always target with multiple pairs, but maybe that's more expensive. We don't want to do that. Or when we want to like introduce a node, like we want to ensure that link, right? So we are working with our partners to like, yeah, how efficiently we can ensure those kind of things, and then put the node back, right? And then again, coming back to validating clusters. So our solution here is Superbench. So Superbench is actually a set of different networking benchmarks and also a set of model benchmarks. So the key idea here is that you can like get the pattern of a particular node, and then based on the pattern, is it actually indicating a particular error signature, right? So if that's the case, then you do the specific benchmarks which are targeting that particular error signature, and then based on that, it is actually taken out of rotation or like maybe put it back for other use cases where those component is actually not needed, right? So those kind of things, and you always keep a historical data of those nodes, right? And the networking side of things, like, yeah, so these are mainly point-to-point based or multi-pair based networks where you can really target particular regions in the network. And you can always get a list of, bad nodes or bad nicks or bad particular links, right? So you can always evaluate, this is the theoretical peak that I should see, but and this is what I got, right? So those kind of things we can do, and then get a list of those nodes. More details are in the Superbench paper in the Usenix 24 this year. So yeah. And coming to the communication library optimizations, so again, Tutel is one of the good examples, specifically focusing on all-to-all based designs. So in this case, what we did was, so instead of like doing an all like any-to-any communication, right? We try to change so that like the communication is mainly within the rail instead of like a linear approach. So you do a two-step approach, but in every step, like you do a shuffle within the NVLink domain, right? So the two advantages: one, you can like keep the communication within the rail, and also you can coalesce the data. So rather than sending smaller chunks, you actually send larger chunks and then get better network utilization, right? Um, We are also looking at like we discussed the rail only topology, right? So we can avoid like super large cost on like merging these rails when that is not required, right? So these kind of designs will really help achieve those goals. Again, another thing is that so designs which are not round trip time based, right? So especially for DCs which are like super long and still participate in a single training job, right? So we cannot rely on the existing protocols, right? Which are like based on an ACK or NAC. So rather, like we have like we are looking into newer designs where they can still talk to each other but efficiently. So with that, let me conclude my talk. We went over some of the scaling and efficiency journey for Microsoft Azure HPC AI over the years. We reviewed some of the key challenges and insights for scaling beyond, like the new routing designs and also the changes in the communication library designs, especially for the long distance or non-RTT based communication library designs. And looking forward, right? I mean, so we see shifts in network topology designs. Right? We talked about the rail only topologies and like new topology designs, which are tightly coupled with the workload characteristics or requirements, right? And we also like see move towards like tight coupling with the communication library and some of the routing choices, right? So yeah, those are the directions that we are looking more closely, and I look forward to working closely with many of you as partners. Yeah, thank you.